Hi friends, welcome back. We are into the signals and systems simplified, the concepts every engineer must master. Yes, signals and systems is an essential component of any electronics and communication engineering stream, and without understanding the basic concepts of signals and systems, it is not possible to do anything in electronics and communication. So welcome to this another session on signals and systems simplified. We are in the first unit where we are trying to understand what signal is, what system is, and how signals can be related with vectors and all that. So in that series, continuing, let us get into the further details. Hi, welcome. I am Dr. Sandeep, your mentor. Now let's see what a complete set of orthogonal functions actually mean. A set of orthogonal functions is complete if and only if any signal in the space can be expressed as a combination of its members. See, we are talking about vector analogy. Then if we are talking about a 3D space, then yes, we do require three orthogonal components of 3D space: x, y, and z. It is not possible to represent any point in this 3D world using less than 3 components. We need all 3, only then accurately we can represent any point on this 3D space. It is not possible to represent with 1 component or only 2 components, but yes, to represent a particular point exactly on a 3D space, we do require all 3 components. What is the component along x, what is the component along y, and what is the component along z? All 3 are equally required, only then it can be correctly, perfectly represented. So that is, in a 3D space, we do have 3 components or the members. So here all these 3 members are orthogonal to each other, so these are called orthogonal functions, and all 3 together will define any point in the 3D space. Therefore, for a 3D environment, a complete set is made up of 3 components: x, y, and z. In the same way, analogy applies to signal also. So when we are talking about a signal, the signal is represented in a particular domain, and that domain will have its own orthogonal functions, and the set of orthogonal functions are used to represent a signal. So a signal can be exactly represented with the number of orthogonal signals, and all orthogonal signals required to represent one signal perfectly is called a set of complete orthogonal functions. So the completeness condition says that if we are talking about a value of orthogonal functions n, then for any signal x of t, we can have an approximation of xn of t using n components of the signal space, and the difference between the actual signal and the approximation signal must be 0. Only then we say that the approximated signal is exactly equal to the original signal, and that is possible with some n number of components, and if all n numbers are used, only then it is called a complete set. So the common complete sets what we usually come across in signals and system is a Fourier. So that is a set of sinusoidal and cosinusoidal functions and their integral values. Then Walsh functions, that is the rectangular versions of that, and wavelets. So these are some examples. for complete sinusoidal. So the complete set of orthogonal functions enables full representation of a continuous time signal, and the basis choice depends on the application. So if we are working on a particular type of problem, then some particular type of basis functions are useful. So in some cases Fourier is useful, in some cases Walsh is useful, for some cases wavelets are useful, and so on. So as an example, we can see that we are trying to approximate a square wave. So we are trying to approximate square wave using the Fourier analysis, where a Fourier is made up of a sum of orthogonal sinusoidals and cosinusoidals. And if we use a single sinusoidal, then I don't think it has any resemblance with a square wave. But when that sine wave is added with a third harmonic, then yeah, little similarity is visible now. But to that, if fifth harmonic is also added, it becomes more closer to the square wave. When the seventh harmonic is added, then it is still more closer to that. So as we keep adding more and more odd harmonics, then we find that the approximated wave, which is shown in the red, is coming closer and closer to the square wave. And this square wave we can get perfectly only when this value of n tends to infinity. That means when we have infinite components, only then it becomes a square wave. So it is very well established fact that the square wave is made up of infinite components, starting from zero frequency goes up to infinite, but all what we call odd components, odd harmonics only, no even harmonics are present here. And of course each time the magnitude of the different harmonics is changing. The first harmonic, that is a one first sinusoidal, is a bigger one. The third harmonic is of almost 1/3 of the earlier magnitude, and the fifth harmonic is 1/5 of the magnitude, seventh harmonic 1/7 of magnitude, roughly speaking. So that way it continues, and this is what we are talking about, a complete set of orthogonal functions. The same way, when it talks about Walsh functions, then we do have the same representation, but now instead of sinusoidals which were used in the Fourier, now we do use square waves of different frequencies, like one with a frequency f, then the other frequency 2f, 3f, 4f, 5f, and so on. So one is f, then other one is 2f, then the next one is 4f, then 6f, then 8f, and so on. So that way we have different harmonics, and these combined together to form different approximations, and that is what we use under Walsh set. Same way, when we talk about wavelets, so we do have different wavelet basis functions. So combination of these wavelet functions can represent any given signal. So that's something to do with a complete orthogonal system. Now let's look at what orthogonality in complex functions is all about. So when we are talking about signals, mostly the signals are complex in nature. That means the signals do have both magnitude as well as the phase. To represent magnitude as well as phase, we make use of complex representation. Therefore, any signal, when we say it is usually complex in nature. And when we are trying to find the orthogonality, so we make use of inner product of one signal with the complex conjugate of another signal. So the orthogonality condition in the complex functions is the integration from minus infinity to plus infinity, and what we integrate is a product of two functions. One is a phi I of t, that is our signal. At every time t, what is the value of phi I, and at the same time t, what is the complex conjugate of phi j? So the phi I value and the complex conjugate of phi j at any given time are taken and they are multiplied, and this product is integrated over time minus infinity to plus infinity. And if we think that phi I and phi j are orthogonal to each other, then it should satisfy this condition that this integral must be 0. So the complex exponentials form an orthogonal set where we talk of e to the power j 2 pi nt over capital T. Capital T is the period we are talking about, and n is the harmonic. If n is equal to 1, we are talking about the basis function. Then n is equal to 2, we are talking of second harmonic. N equal to 3, we are talking of third harmonic, and so on. So if we look at e to the power j theta, in reality what we are talking about, e to the power j theta is a vector which is rotating, a unit vector which is rotating, and at any given time we say that the angle of that vector is theta. The angle between that vector and the x-axis is theta, and that's what we mean by e to the power j theta. Now we are having e to the power j 2 pi nt. So that means as time is increasing, then this vector is changing its position. The theta value is increasing with time t, and one revolution is given by 2 pi n over capital T, that is one period what we call. And so you can visualize this as e to the power j 2 pi n over capital T times small t. Small t is the running time, and this represents a rotating vector of size 1, and any given time the angle is 2 pi n over t times t. So that's what we have is an exponential signal, and here n is an integer. N equal to 0, it means a constant. N equal to 1 is the first harmonic, n equal to 2 second harmonic, and so on. And all these are orthogonal to each other. So from n equal to 0 to infinity, we do find infinite exponentials, and each of them are orthogonal to each other. So we can say that it's a complex orthogonal set. And this orthogonality in complex functions is very much useful when we are working in frequency domain analysis, as we discussed earlier sometime. It all depends on the observer's speed of visualizing the situation, how fast the observer can visualize. If the observer is slow compared to the speed with which the actions are taking place, and if that action is a periodic one, then definitely in a given period of time we can count how many revolutions it took. So we can talk in terms of frequency domain. And if what is happening, the natural phenomena, what is happening, if it is slow compared to the user's perception, then we can identify at different time where that thing was. So now we can work in time domain. So this orthogonal complex functions are very much useful when we are working in frequency domain, and it very much simplifies the frequency domain analysis for any signal or any system, or in general for any signal and system, or a signal if it is passing through a system, and if we are working on complex signals, complex functions which is representing either a signal or a system or both, then the frequency domain analysis is the best one. And the exponentials which are orthogonal to each other, a complete set of complex functions which are orthogonal to each other, are going to help us in understanding, analyzing either signal or system or both. The Orthogonal complex functions are very much used in Fourier series and Fourier transforms. Fourier series and Fourier transform make use of two types of signals. One is a sinusoidal and other one is a cosinusoidal, and they are emerged out of the exponential. So the exponential functions, that's a complex functions, can be used in the Fourier series and Fourier transforms. So let's just check what orthogonality is in our normal sense. So if z is any vector, it's represented in the polar domain as r, that is the length of the vector, and e to the power I theta, where I is an imaginary number, root of -1, and theta is the angle between the vector and the x-axis. Its complex conjugate, if you look at it, z bar, that is r e to the power minus I theta. This was e to the power I theta, this is e to the power minus I theta. That is a mirror image of the vector along the real axis or the x-axis. So here, if we find the inner product of these two, then what we get is a real quantity, that is r square. That's what we are trying to find that. And if the two functions are orthogonal to each other, then this inner product must become 0. That means if this theta between these two is 90 degree, then we get a answer to be 0. So let's take up this example where the red one is a sinusoidal and the green one is a cosinusoidal, and we know that sine and cosine are orthogonal to each other. So if we multiply them, then what we get is the yellow one, and integrating that over a period, so we find that the shade positive part and the shade negative part are always equal. So when we integrate from minus infinity to plus infinity, the positive area, negative areas are always equal, and hence the overall, the net area under the curve is 0, because we know that cosine and sine are orthogonal to each other. Same way we have seen in previous session that sine and another sine which are harmonically related are again orthogonal. So two harmonic cosines are orthogonal. So in general we can say that sine is orthogonal, cosine are orthogonal. That is because the basic thing, which is a exponential, is basically an orthogonal. Okay, now we need to know what is not orthogonal. So let us take an example of cos 3 pi x, which is given by the green one, cos 3 pi x minus so we have one cos 3 pi x which is in the green, and cos 3 pi x delayed by pi by 4, that is there is a 45 degree delay, and this delay, because of 45 degree delay, we cannot claim that they are orthogonal, because if the delay was 90 degree, then sine would have become cosine and cosine would have become sine. But because of this 45 degree delay, if you multiply them, then what we get is the blue curve, and if you look at that, then the positive part is more than the negative part, and when you integrate that over time, then they don't cancel each other, and hence the overall integration will not be 0. So the overall integration not being 0 just indicates that these two functions are not orthogonal. So just as an example, I was trying to show what orthogonality is. We can talk about exponential function as an orthogonal function. Exponential function can be split into the real part, which is a cosine, and the imaginary part, which is sine, and because the exponential is orthogonal over the different harmonics, the same way as cosines are orthogonal over different harmonics, same way sinusoidal are orthogonal over different harmonics. So cosine is orthogonal, sine is orthogonal, so the combination of them also is orthogonal. So that way we can say that the exponential is an orthogonal, and it is a complex form, and the value of n is from 0 to infinity, and all infinite components together will form a complex signal space, and any signal can be represented as sum of these signals, sum of these orthogonal complex signals, orthogonal exponentials, and all these things are going to simplify our frequency domain analysis. So that's it for now. Thank you.